A modern skyscraper is a marvel of concentrated mass. You have thousands of tons of steel framing, dense concrete floors, and glass, all stacked hundreds of feet into the air. We trust these towers with our lives because we know exactly how those materials behave. Steel and concrete are manufactured in controlled environments. Their limits are tested in labs, and their structural math is highly predictable. Every single ounce of that weight is channeled downward. The floors transfer the load to the beams transfer it to the columns, and gravity pulls all of it straight down into the foundation. This photograph shows an excavation site sitting right next to completed high-rises, highlighting the exact moment the engineered perfection stops. At the very bottom of those concrete pillars, all of that carefully calculated weight is handed off to raw, unengineered earth. Our most precise, mathematically rigorous structural achievements rely entirely on nature's most chaotic and unpredictable material to hold them up. If you ask an agricultural scientist, the ground is a medium to grow plants. To a geologist, it's a physical record of weathering rocks. But neither of those definitions helps you when you need to park 50,000 tons of concrete on top of it. To a civil engineer, soil is a highly sensitive structural problem. It is a loose, unconsolidated mixture of inorganic material that is incredibly vulnerable to shifts in weather and moisture. For centuries, builders treated the ground like it was a solid, uniform block. They relied on trial and error. This photograph of the Leaning Tower of Pisa shows exactly what happens when you misjudge the loose, shifting layers hiding beneath heavy stone. The foundation sinks unevenly, and the structure fails. Preventing that kind of collapse requires a specific discipline. It's called geotechnical engineering, and it is the study of how soil behaves when it is used as a foundation or a construction material. To keep our cities standing, engineers had to figure out how to mathematically tame the dirt itself. The first step in that math is realizing that the ground beneath your feet is not actually a single solid mass. This diagram illustrates what engineers call a three-phase system. If you zoom in close enough, soil is a chaotic mixture of solid rock grains, liquid water, and trapped air filling the empty void spaces between the particles. The stability of the ground depends heavily on the water phase. Engineers measure this using Atterberg limits, specific moisture thresholds where the soil transitions from solid to plastic and eventually to a liquid state. As more water fills the voids, it literally pushes the solid grains apart. This creates a massive problem for construction. When the void spaces become saturated with water, the soil loses its ability to hold a shape under pressure. It turns into a sliding paste. The structural integrity of the ground doesn't come from the solid dirt alone. It is dictated by the invisible, shifting ratios of the water and air trapped inside it. To prevent the ground from rupturing, it needs shear strength. This is the internal friction and cohesion that keeps the individual solid grains locked together when a heavy load pushes down on them. If the natural ground doesn't have enough shear strength on its own, engineers artificially force it to be stronger through a mechanical process called compaction. This animation shows how compaction works. By applying heavy vibration and pressure, engineers violently squeeze the air phase out of the soil. Without those air gaps, the solid grains are forced into a tighter, locked matrix. This approach to manipulating the ground was systematized in 1925 by Carl von Terzaghi. He proved that the strict physical laws of mechanics and hydraulics could be mapped onto these particles, finally allowing builders to calculate exact settlement rates and bearing capacities. By managing the microscopic phases of air and water, raw, unpredictable dirt is transformed into a highly reliable structural earthfill, capable of supporting thousands of tons without buckling. But calculating the support for a static, resting building is only half the battle. The real test happens when things start moving. This is the specialized field of soil dynamics. Look at the sheer devastation in this photograph of earthquake damage. Sudden dynamic forces, whether from the rhythmic pounding of heavy industrial machinery or the massive shock waves of a seismic event, inject huge amounts of energy directly into the soil grains. Under severe shocks, fine, saturated sand can undergo a process called liquefaction. The vibrations disrupt the friction between the particles, the pore water is pressurized, and the compacted soil instantly loses all its shear strength, behaving entirely like a liquid. Preventing that kind of microscopic failure is what actually allows us to build the macroscopic world above the surface. The next time you walk past a soaring steel skyline, look past the glass and concrete. The true mastery of modern civilization is hidden underground, in the precise mathematical control of the dirt that holds it all up.